Hi, it's time for another math easy solution. Time to discuss further into applications of integrals and further into moments and centers of mass, which is part of the applications of integrals to physics and engineering video series that I've been going over lately. And now look at uniform density as opposed to mass this at specific points. And again, make sure to watch my last couple of videos on moment centers of mass, which I go over an introduction as well as a simple example. But those ones we didn't use integrals, we didn't need to use integrals, but in this one we will need to use integrals because we're dealing with a uniform mass or density as opposed to mass at a specific point. So basically in my earlier videos I went over determining the moments and centers of mass of basic mass at specific points. But this time we will consider a flat plate called a lamina. I'm not sure why it's called that. I think it's because laminated. Anyways, so basically it has a uniform density rho that occupies the region R of the plane. I'll draw this out later on in the video. And we wish to locate the center of mass of the plate, which is called the centroid of R. And in doing so, we use the following physical principles. And the first principle is the symmetry principle, which says that if R is symmetric about a line, then the centroid of R lies on L. The centroid of a rectangle is its center. For example, if we were just to draw a rectangle like this, the center of mass or the centroid of this, let's draw the lines of symmetry. There's multiple lines of symmetry across this. So this is line of symmetry L of this rectangle. So this region R, let's say that's R. So let's say this whole region is R. Then obviously the center from this side has to be on this line. And then if you look at another line of symmetry, doesn't matter how many you draw. So now it has to be on this line. So it has to be on both of these lines L as well as if you were to look at across this way. So it's symmetric about that line as well. So it doesn't matter if you look left or right, rotate, it's going to be the exact same thing, as well as drawing across here. So it's on any line of symmetry, has to be on that point, and then it turns out to be the very center of this rectangle, and this is called the centroid. Now the second principle we're going to use is basically moments should be defined so that if the entire mass of a region is concentrated at the center of mass, then its moments remain unchanged. Again, recall from our last videos, I discussed what moments were basically, and I also illustrated a bit that when we have, let's say, a region like this, so if we're determining the moments about this line, or actually let's say about a line like this, so if we're determining the moments about this, or the tendency to rotate about this, we'll call this just M like that. And if this has weight all across it, so this is the region R, so the total moments of this entire mass, if we were to concentrate this all into one point, which would be the center of mass right here, we'll call that C for centroid. So if we took this entire mass M and put it into one point at the centroid C, then the moment is going to be the exact same. So if this entire mass is put onto this one point, we'll have the same as when you it will have the same as this entire region when you solve for the moments about this one. And that's basically the whole idea of center of mass, is moving that center and moving the entire mass up to a center which has basically the same moment. That's pretty much the definition of moments and centers of mass. And then the last principle we're going to go over is the moment of union of two non-overlapping regions should be the sum of the moments of the individual regions. What this means is again similar to the second one, where if you have, let's say you're taking the moment about this, so finding the moment there, and then you have two non-overlapping regions like this. So then when you took each individual, so you want to find the full moment about this, again you'll look at the centroid. This has to equal the same exact moment applied, if we were taking it about this line M, this would be the same as the addition of the two. So you would take this center of mass, find the moment, so this full moment right here would have to equal to, let's say we had 1 and 2. So the moment I'm just drawing this as it's because it's going to be mass times the length. This is going to be M, oops, right here, capital M, which would be a summation of both of the moments. So these have to be the exact same. So that's the principal third one we're going to use. So now let's go ahead with the region. So the region I explained above here, so we're trying to find the centroid of this region. Let's say supposed region is of the type shown below. So let's say we had this x and y axis, and we had the region that looks something like this. So this is our y equals f of x, like that. And this is up to from x equals a to b, and then this whole thing, it's positive and it's above the x-axis. This is our region R, like that. And we're trying to find the centroid. And now, like my other videos on integrals, we have to divide this up into, we divide this interval from a to b into n subintervals with endpoints x0, x1 all the way to xn, and equal with delta x. And then we choose, I'm just going to add the dictionary. So we choose a sample points xi star to be the midpoint. We'll call this xi with a line above of the ith interval. That is, well, let's just draw this out. So basically this is similar to all my other videos on applications of integrals and integrals themselves, how we define them. So if we were to draw this shape again, just so I could apply that, so it looks something like that. This is at A, like that. This is at B. So we're going to break it up into rectangles, a bunch of them. Yeah, so now if we were to draw these out, let's just draw these rectangles again. The sample point is basically the point that's going to connect to the f of x line, and that is our xi star, which is going to be xi with a line above, which is the center line. So we're picking the center line. So if we take the interval, the first one is going to cut through the center like that. And we'll have this across all the way here. We'll call this R1. And then again, it's always through the center. That's what we're picking. We could pick at anything in between. So this is going to be our R2. And this is our X0, X1. This is X0 is A. This is X1. X2, and the center line is the the center line is what connects to this point. So let's draw another one here. Let's just keep drawing these out like that. I'll draw this like that. It's not the scale. Keep going. Whoops. This goes like this. So it's something like that. So we have all that, and this one all the way up to here is our xn, and this is, let's say, R3, and again you have R4, R5. These are all regions, subregions of this entire thing, and again the width of every single one is a delta x. So if these are x0, x1, x2, let's look at a generic xi. So let's pick this point here. I'll put this in black. So we'll call that xi, and then the one right before it is our xi minus 1. And then the center line right here, this is at our center point we chose as our sample point. This is xi with a this is our xi star sample point, which equals 2xi with the line above. And at this point right here, this height, that is again, because we chose simple as a center, so this is at xi center, and then f of xi center. And now the centroid of this section right here, this xi point right here, or the ith Yeah, ith subinterval or rectangle Ri is, I'll just write that down right here. This is our Ri. So this region is our Ri. Is by symmetry by the symmetry principle, it's its center C1, actually Ci. Yeah, I just corrected that. So it's Ci which lies on the point. We'll get to that. So basically this is a rectangle, and again we just already illustrated that the rectangle has it at the center, is where its center of mass is located on. So that's going to be right here, and we'll call this Ci. So this means that, well, the center point of this Ci, that's just, well, that's going to be, it's going to be at xi. So the point is xi center, center line like that. And then we put in, this is, well, the full length is f of xi center line, but now it's the half of it. So this distance across is 1/2 xi center, and so then we'll just put 1/2 right here. So this is a half of that point, that full length right there. So we know the center line of this small subsection, and because it's a rectangle, so we're approximating using rectangles, so we could find the center line point. Yeah, so the center point is our center of mass for that point. And now what we could also solve is the area and mass of this ith rectangle, and they are thus, well, the area is just the area of a rectangle, so that's going to be, that's simply delta x, because we know it's all delta x times it by the full length, which is going to be f of xi center line times it by delta x. And now the mass of it, this is the interesting part. Now the mass is technically equal to, well, the density times it by the volume. Let's go mi times it by volume of this. That's because this rho is units of mass over so it has units of mass over volume. So we need to multiply by volume to get it. So we're gonna, basically the idea is to assume this has a so if we were to assume that this region, let's just has a height h or thickness h like this. This is just to be technically correct, but you'll see that it doesn't matter. So if we have, let's say assume it's perfectly like that. Let me try this a bit more. So if we assume that this has a height like this, constant thickness h, or constant height h, then its volume right here, and then its mass is going to be equal to rho times it by, well, the area of the region. It's going to be an area times height times it, yeah, the area times height for volume. So for this subsection we'll have ai times it by, well, h, since it's constant. But again, since it's constant, what will end up happening is that this height will eventually cancel out. So instead of just dealing with technically the mass, let's just deal with unit mass, because in this example we weren't given that this one's, again, is assumed it's constant, so we weren't given a height or thickness of it. So if we just assume it all like that, so in actuality we'll be dealing with a this is going to be, we're going to be dealing with instead this rho right here. Instead of mass per volume, we'll go for a unit density, where its rho is going to be a mass over area, and again where over assume that it's just a unit, or this is going to be 1 unit thickness. So basically the idea is, I'm just saying, just ignore this part here and deal with the unit density. We'll just call this rho times it by area I. And again, I'll show you later how the h will cancel out anyways. And in fact, this will cancel out anyways when we find a center of mass, because it doesn't matter how thick it is. I mean, how dense it is. It's always going to be the same centroid. So now that we got that out of the way, so the mass is going to be rho times AI. And again, if you need questions, just let me know, comment below. Further clarification on this topic. So now we have rho times, this is going to be f of x I center line times delta x. That's simply this part there. Yeah, so now let's go ahead and start solving the moment. So the moment of Ri, the region of that rectangle, about the y-axis is simply the product of its mass and the center, and the distance Ci, or centroid, to the y-axis. So if we were to draw that part out, since we're dealing with only, let's see how it looks like again. I think it's like that. Just to draw it like that. So this point across here is our I. Draw this a bit better. So at this very point, if this is our Ri, again this is a y-axis, so we're dealing with the rotation about it, or my, and we'll call this my of the region Ri, like that. So it's going to be the mass mi times it by the distance to the centroid here, which is going to be our xi, like that. So thus we have, for this one region, we'll call this as a function of the whichever region you're dealing with. So again, this is at this point here. This equals to mass mi times it by the distance xi center, or centroid of that. And then again, that's by definition. So now we could just plug these in. And this equals to, well, we know the mass is rho times the area, which is fxi, like that, times it by delta x. That's our mass, times it by, now we have this point, xi center line. Let's just write this a bit neater. So this is going to be like that, times it by fxi center line delta x. So that's what we have. So now we're going to add up all these moments, and then again, like always when I deal with integrals, then by taking the limit as n approaches infinity, we obtain the moment of r about the y-axis, or the total r. And again, this is part of the part 3 principle, and we're going to sum up the two different moments to get one of them, like that. And again, that's also the same thing as the second one here. When you take this full region, all the moments, but again they'll be broken down, we get one moment, we get a moment that's equal to the summation of all of them at one specific point, which is a centroid. So what we have now is the full moment about the y-axis, or the tendency to rotate about the y-axis, is going to be equal to the limit as n approaches infinity of the summation of all of these moments, like that. So at I equals 1 up to n, and I'll write like this. This is going to be rho, this is this part right here, times, actually I'll write this first. I'll write my, and then this is going to be our Ri, like that. So just for completeness. So let me plug those in. So again, we're summing up every single region. N I equals 1. Now we have rho xi center line f of xi delta x. And again, when you sum this all up, we get an integral. This by definition is a Riemann sum. And then we sum, when you sum it up like this, we have infinitely many subsections. So then this delta x will be infinitely small. So we get this equals to an integral. And then again, this is a constant, so we can take it out. So it's like that, integral from a to b of, and now this center point, this is going to be so small. I mean, this is going to be so small that this coincides with xi and xi minus 1. So again, like always, that just equals to x. F of x, and then we have dx, like that. Yeah, so there is our moment about the y-axis. And now in a similar fashion, we can compute the moment of Ri of that region about the x-axis as a product of the mass and a distance from Ci, because we're dealing with a two-dimensional shape right here. From the distance, centroid to the x-axis. So again, if we were to draw this out like that again, let's draw this a straighter line. Something like this. This is B, this is A, this is our Y, this is our x-axis. Now we can look at the tendency to rotate about this axis like that. So when we look at that shape again, let's draw it like that. This is our ith interval. So this has region, this is a region Ri. So now the tendency to rotate about it is, we know the center point about this. So that's going to be, well, this mass, again we have mi, times it by, now it's the distance across to this point. So that's going to be the distance, this is our, alright, this is our xi, this is our xi minus 1, and this is our xi center line. So the distance from here to here is a centroid. This is our ci, and this is going to be 1/2 of f of xi center line, which is, this is our f of xi, like that. So that distance times by the mass is going to be the moment mx, and this is going to be of the Ri region. So we could write that down as mx, or the moment of this region about the x-axis. This Ri region is going to be equal to the mass of that region times it by the distance to its centroid from the x-axis, which is 1/2 f of xi center, or center line. So again, now we could plug in what we know. We know this mass is just density, or rho, times it by the area, which the area is going to be, recall the area is going to be f of xi, like that, times it by delta x. Now we multiply by this 1/2 f of xi, like that, center line. Now we could simplify this further. It's going to be 1/2 times rho, and then this is going to be square. We could square these, so this is going to be f of xi center line squared, and then delta x. And again, likewise, we could just add these moments using the third and second principles illustrated above, and then take the limit to obtain the moment of r about the x-axis. So the total moment mx about the x-axis is equal to the summation as the limit as n approaches to infinity of the summation of all of these intervals. This is up to n, where I equals 1 up to n, and then again we would write mx of the R'th region. So we sum up to infinitely number of regions that are infinitely small, so n to infinity, and then this is like that, and I equals 1, and let's just plug in this formula. 1/2 times rho, or density, times by f of x I, like that, squared delta x. And again, this is a Riemann sum. We could write this as an integral, so we finally get mx equals 2, and this is 1/2, and this rho are constants, to take those out. So 1/2 rho, and then we have the integral. We have the integral from, this is a to b of the full region, and then we have right here f of x, and again, since xi center line is, since delta x is super small, infinitely small, this xi, the center of it is going to be roughly equal to the both endpoints, xi and xi minus 1, and we'll call that x, and then dx for infinitely small, and then this is squared. So we square this whole thing like that. So that's the formula for that. Yeah, for this moment, and I'll just circle this one like that. And again, just for the system of particles in my last videos, the center of mass of the plate is defined so that if we were to take the mass and put it at one point multiplied by the centroid in the x direction, this is going to be, has to equal to the total moment, or this is the my about the y-axis, And similarly, the mass of that full plate times it by the centroid in the y direction equals the moment about the x-axis. And again, this is also part of the principle 2, where you basically take the entire region, put it into one point, and that has to be equal to the same moments as the summation of all of them. So, and then also the mass of the plate is again the product of its density and its area. Well, it's the unit mass, like I explained above. So we have mass equal to this rho times by area, and we know that the area of the region, we already know how to solve areas from my early videos on integrals and areas. That's the integral of from a to b of fx dx, so that's the area. So we have that, so thus we can solve for each of these centroids. So we have thus the centroid in terms of x is equal to, just rearrange that, my over m, which equals to, let's find our my, which is, so our my is right here, rho times integral from a to b x fx dx. This is going to be rho integral from a to b of x f of x dx divided by the mass, which is right here, which is rho integral from a to b of fx dx. And again, like I explained above, you were actually going to cancel out these densities right here. And in fact, even if we had the not just the unit density, if we included our h, so if we had the thickness of the plate, assume it's constant, because if it's not constant, we're going to be more complicated to solve. But if it was constant, well, we would include that inside the above equation, inside the moments, because it was a mass times by the distance. So then, and also be at the bottom here as well for the mass here. So in fact, if we included them, we'll just cancel out anyway. So we end up getting right here integral from a to b x f of x dx, divided by integral from a to b of f of x dx. Yeah, and then now likewise for the y and the centroid in the y direction, this is equals to, just rearrange this formula, mx over m. So the moment of the moment about the x-axis divided by the total mass, this just equals to, well, we already know this, that is 1/2 rho fx squared. So this equals to 1/2 rho integral from a to b of fx dx. Again, if we include the h, it's still going to all cancel out. So even here we have rho, I'll just erase this just for show. Like that. This is to say if we included it, doesn't matter. We'll still cancel. Now divided by the mass, rho times a to b, and again put this squared like that. F of x dx. Again, the rows cancel, or density cancels, so we end up having a 1/2 integral from a to b of f of x squared dx all over integral from a to b of f of x dx. Yeah, basically again, notice the cancellation of the densities. So this basically means the location of the center mass is independent of the density. Again, if it's a really light plate or a heavy plate, it doesn't matter. The center of mass can be the exact same, as well as if the thickness was the same, won't change anything. So again, now in summary, the center of mass of the plate or the centroid of the region R is located at the points x and y center line above, where basically these, just to summarize, you could write this as 1 over area. So we'll just write this in bottom integral as just area. And then for the x1 is integral from a to b of x f of x dx. And then for the y direction of the centroid, this equals to 1 over a, the area as well. Again, now we have integral from a to b, and I'll split the 1 over half inside here just to make it look like the above equation. And then we have f of x squared dx. So that is the center of mass, or the centroid of the region R. and those are the formulas in terms of integrals. Anyways, that is all for today. Hopefully you learned from this pretty extensive proof video for the formulas of center mass of a region like this. And yeah, and also just one more point right here. If this is constant, it won't change the center of mass. But if you have, let's say, Vs, or just say we had something like, I'll put it in a bubble just to illustrate it, not too big. If you had a shape like this, and then let's say the thickness changed, so let's say it was a curve like that was the thickness. Okay, something like this. Then this would push, if this was the thickness, it would push the centroid all the way down. Because yeah, just think about it, you're trying to balance it out. So if all of the weight is down here, then obviously you are going to, I'll just draw it a bit better like that. Then obviously it's going to change here. So this thickness will change it if it's not constant. If it's constant, it won't change where it is, nor density. But this one here will change it. So yeah, that's just an illustration where if it's not constant height, you're going to have a different center of mass. But we won't deal with that right now. It's a bit more complicated. Anyways, all for today. Hopefully you learned, and again, like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.